So in this example 1.8, we see a typical treatment of a sequence. Here's a sequence xn defined by this formula here, 2/3 of 2n squared minus n divided by minus 3n squared plus 2. Okay? So it's a bit of a convoluted description of a sequence. And there's a typical little argument here, and I know some of you spoke to me about this before, about rules for dividing above and below by the highest power of n. So you may have seen these kind of arguments before. Let's just have a look at how the argument goes. We are searching for the limit of xn, so this is the limit of this expression here. That's what xn is. The first thing we do is this factor of 2/3, we take that outside the limiting process. Because we're saying that the limit of 2/3 times a sequence is the same as 2/3 times the limit of the sequence. Okay? This multiplication by the factor 2/3 can move outside the limiting process. The second thing we do is we've somehow re-expressed our fraction by dividing above and below, dividing numerator and the denominator. Dividing the numerator and the denominator by, what did we divide by, n squared. That doesn't change the value of the fraction. If you multiply above and below the fraction by the same quantity, you haven't changed it. So this is still the same, the limit of the same thing. But what it does prepare us for is an ability to use what's called the quotient. In the next step, from the second line to the third line, the justification is we're saying that the limit of a quotient is the quotient of the limits. The limit of the sequence element, or the sequence element, is defined as a smaller subsequent, or a simpler sequence divided by another sequence. That's what we're looking at here. We've got a sequence in the numerator, a sequence in the denominator. We're saying the limit of the quotient is the quotient of the limits. And then finally, we look at this thing, the limit of 2 minus 1 over n, and we already know that the limit of 1 over n is 0, so we proved that. Okay? And one of the tutorial exercises was to prove that the limit of 1 over n squared is also 0, using the formal definition of convergence. So using those two facts, we can say the limit of this constant minus the sequence 1 over n, that's going to be just a constant value 2. And the limit of this combination down here, minus 3 plus 2 over n squared, well, that's minus 3. So finally, then, we can just evaluate out the limit. And it appears that the limit of this sequence is minus 4 over 9. Okay? So that's a typical way of treating a sequence. It can more or less be applied to any sequence that's defined by a rational function of n. Okay? So a rational function of n means a quotient of polynomials. Okay, a rational function of n is a quotient of polynomials. One polynomial in n divided by another. This approach can more or less be applied to any such sequence. But what I want to emphasize to you here is this argument is using knowledge about how the limiting process behaves. Okay? Knowledge that we should initially be slightly wary of, or not necessarily suspicious of, but yeah, critical of. Okay? Who says that if you've got a limit of 2/3 times something, that's going to be the same as 2/3 times the limit? It does seem correct. It does seem intuitive. It does seem like a nice result. But we haven't proved it yet. We've seen no direct evidence of it yet, if only just how it feels in our minds. Who says that the limit of a fraction of things is the fraction of the individual limits? Okay? This argument is claiming it can do that, but as mathematicians, we should be extremely critical about using a property like that. Who says that the limit of the difference between a constant and a sequence 1 over n, if you know what the limit of the sequence is, who says that that's equal to the value of the constant plus the value of the limit? Here, the value of the limit is 0, so you get 2 zeros, you just get 2. So this is using properties of how the limiting process behaves. But what we should be concerned with as mathematicians is making very sure that those properties are correct. An engineer or a physicist would be happy enough with this explanation of, I'm just being told that that's how the limiting process behaves. But we should be concerned with proving these properties. Now, as we said in the early lectures, the question of convergence and divergence is very important and central in mathematics. It arises in almost all mathematical modeling situations where we have to use approximate numerical algorithms to solve problems. Because when you're using approximate algorithms to solve problems, you're very concerned with the errors, or the approximation errors that arise. And you have to know that you can control and describe those approximation errors and know that they're small or know that they converge to zero, etc. Okay? So if we just play fast and loose and just start, allowing ourselves to use all these properties of the limiting process without being sure about them, we run the risk of making mistakes further down the line. Okay? So there's an awful lot of theory and methods and results built on top of these foundations of how the limiting process works. Okay? So we need proofs of all of these properties. So our main task, what's in our science at the moment, is this theorem 1.4. It's called the algebra of limits. And this proves all the properties that were being used in that example. We're going to prove these using the formal definition of convergence. The reason why we need the formal definition of convergence is because it gives us the tools and the ability to speak precisely about convergence, which will allow us to prove it. Let's just look at the statement of the result. It imagines that we have two convergent sequences, an and bn. An is converging to the limit a, and bn is converging to the limit b. So we've got three results here. We've got a result about linear combinations. It says, how can we take the limit of a sequence which is defined or made up of as a linear combination of the sequences an and bn? So inside the round brackets there is a new sequence whose nth term is alpha times an plus beta times bn. Okay, that's a new sequence, and this result tells us that, well, it is a convergent sequence, and it very nicely it has the limit, which is alpha a plus beta b. Okay, that property is being used in that example we just looked at, where they said the limit of 2 minus 1 over n is 2 minus 0. That's an example of where they were using the linear combinations. But we would require a proof. Second one is about products. In the round bracket there is a new sequence, a sequence whose nth element is an multiplied by bn, the corresponding elements from the two sequences. This property says, well, the limit of this new sequence is the product of the two limits. Very nicely, very intuitively, unsurprisingly, but it's still, just because something is unsurprising or seems to fit with our intuitions, we shouldn't go believing it just because of that. Okay? We need rigorous proof for these mathematical properties. And the third one is just a similar property, but this time regarding the operation of putting things in quotients. So again, in the round bracket there, in the third property, we've got a new sequence whose nth term is defined as an divided by bn. Now, when you're dividing by stuff, you have to be careful to avoid 0. So assuming that none of those bn's are 0, assuming the limit b is not itself 0, this property says that the limit of this sequence is simply a divided by b. So that's what theorem 1.4 says. So once we have theorem 1.4 proved, once we have that in our arsenal, we'll be able to safely and confidently perform calculations like we just saw in example 1. Okay? Because we will know true mathematical knowledge that this is how the limiting process behaves, and so we can use that with confidence and be sure of the results that it gives us. Okay, any questions about the statements of those results, or just about what we've been talking about About the calculation in example 1.8, is there any aspect of that you'd like me to clarify or say something about? It's important to, I think it's the reason I'm introducing it slowly is to try and give you a good understanding of what it is we're about to embark on, what these proofs are for, and some of the reasons why we require it. Okay, let's get to it. But first of all, we're going to pause slightly and just prove one which I think we'll need further on, which is this theorem 1.2. Theorem 1.2 says every convergent sequence is bounded. I'm going to quickly sketch out the proof of that here. Every convergent sequence is bounded. Now remember, what's a bounded sequence? We gave the definition bounded. A bounded sequence is one where there exists some number, perhaps a large one, m, and the whole sequence, x1, x2, etc., the whole infinite sequence is contained within that interval. That's what's called a bounded sequence, one that you could trap within a lower and an upper bound. Okay, so that's just a quick picture to remind you of the definition of bounded. Okay, an unbounded sequence is one that you can never contain in an interval on the number line. So an unbounded sequence would be one that is increasing forever without any upper bound. You just get arbitrarily larger and larger elements. You could never set down an interval that completely contained the sequence. That would be an unbounded sequence. So theorem 1.2 says every convergent sequence is bounded. Okay? So we give ourselves a sequence xn. We suppose that it converges to x as n tends to infinity. So our task now is to find this number, capital N. And the only thing we can use is the knowledge, the fact, that the sequence converges to x. Well, somewhere on the number line is the number x, the limit of this sequence. And we can set down, what we do is we give ourselves a value of epsilon. I'm going to choose epsilon equals 1, so we've got x plus 1 and x minus 1. So there's an interval on the number line, and we know because of convergence, because xn converges, sequence converges, there exists some number an integer n. I'm letting epsilon equals 1. There exists an integer n1 such that if n is bigger than n1, that implies that the distance from xn to x is strictly less than 1. There I'm just quoting the formal definition of convergence. Why did I choose epsilon equals 1? There's a little side note about that. There's no significance to 1. All I'm doing is just choosing one value of epsilon. That sets down some interval. And now I know that the infinite tail, most of the sequence, beyond the point capital N1, the sequence lies inside this interval. I.e., if n is bigger than n1, that implies that the value xn is an element of the interval from x minus 1 to x plus 1. So we've tracked most of the sequence. Most of the sequence we know is inside this interval. So that leaves only a finite, but maybe x1, x2, up as far as x. So the one before this applies, which will be xn1 minus 1. So that's all in the subscript of the x. the element of the sequence at position n1 minus 1, maybe these are not an element of this interval. Remember, I'm trying to bound things. So maybe these are large, okay? But the thing is, there's only a finite number of them. There's only a finite number of them. So we can... So if we let our capital N be equal to the maximum value I maybe need a bit of a correction in the notes. I'll have to take the absolute value of all of these, I think. Yeah. Actually, we need absolute value signs around all of these elements. 1 plus the absolute value of x. So sorry, correct that in your notes, because in the notes I left off the absolute value signs. In the notes, these absolute value signs. So I'm considering the maximum possible value, maximum possible absolute value that the sequence elements x1 up to xn1 minus 1 might have. And then I'm looking at 1 plus the absolute value of x. Now 1 plus the absolute value of x is the larger of these two edges of the sequence here. The reason I have to consider absolute value of x is I'm not sure whether x is a positive or negative number. I don't know if 0 is to the left here and x is positive, in which case x plus 1 would be the bigger one. Or it might be that 0 is to the right, so x is a negative number, so in fact x minus 1 would be the one which is the largest size in absolute value. So I can get around that by just by considering the maximum. Considering 1 plus the absolute value of x. That will be the absolute value of whichever one of these is the largest. But with this choice of n, then it is true that for all n bigger than or equal to 1, so for every position in the sequence, the absolute value of the sequence element is going to be less than or equal to this number, capital N. So we have found a bound for the sequence. Okay? We have successfully found a bound for the sequence. So the sequence is and the only fact we used about the sequence was that it was convergent to some limit. Okay? So that's and again, it illustrates the use of the formal definition of convergence. We use the formal definition of convergence up here. We chose a value of epsilon, and because it was convergent, we knew there existed some point, capital N1, such that every element of the sequence beyond capital N1 was trapped in that interval, this interval from x minus 1 to x plus 1. Okay, so that's one nice result. Let's move on. We'll skip theorem 1.3. I'll say I'll be doing some examples tomorrow, and I'll speak a little bit more about theorem 1.3. Let's move on to our algebra of limits theorem. First of all, any questions about that proof, or any requests for clarification of any of the points in it? So we first of all successfully bounded most of the sequence inside this interval, all but some initial set of elements, and then we just considered, well, everything's bounded in there. If one of these has a larger absolute value than the edges of this interval, we can take that as our maximum bound. So I just let n be whichever of these numbers is the biggest one, then everything in the sequence will be less than equal to n. So the whole sequence will be bounded. Let's go for algebra of limits. Now it comes in 3 parts, so we'll prove each one separately. So the first one is the linear combinations version. And what are we working with? We're working with two convergent sequences. These be convergent sequences. With AN converging to A, BN converging to B. So I name the two limits as A and B. So theorem 1.4 claims that the limit of alpha AN plus beta BN is alpha A plus beta B. Okay. So given any epsilon greater than 0, so I'm just introducing the proof now, just setting out exactly what we have to do. We have to find a point n, capital N, such that for every value of the index little n bigger than or equal to capital N, the absolute value of alpha AN plus beta BN, the difference between that and the claimed limit has to be less than epsilon. That's what the formal definition of convergence requires for us to be able to say that this sequence, alpha AN plus beta BN, is convergent to this limit. Given any epsilon bigger than 0, we have to find this point capital. Magic it up into existence somehow. Of course, the things that we're going to use, the facts that we're going to use to produce this special point, capital N, given any epsilon, is the known convergence properties of the ingredient sequences, AN and B, that are the ingredients of this new sequence. So, okay, I'll maybe, I'm not presenting it exactly how it is in the book, I'm just, because maybe we should investigate, since we have to prove something about this absolute value, maybe we should pause for a moment and investigate this absolute value. So let's investigate this absolute value. This one here on the left-hand side of the inequality. Okay. There's a natural, helpful way that I might rewrite this. There it is. At the moment, the ANs and BNs are mixed up here, and the A and B are mixed up there. I can rewrite it in a nice way that packages up the AN beside the A and the BN beside the B. So that there is just an algebraic rearrangement of the contents of the absolute value. Alpha AN minus alpha A, you factor out the alpha, so it's alpha times AN minus A. And then you've got beta BN minus beta B, so you factor out the beta, so it's plus beta BN minus B. Now we're going to have to show that this absolute value is less than something. And there's a very important property of absolute values called the triangle inequality, which we used before. We used the last time when we were doing the uniqueness of limits. The triangle inequality says that if you've got the absolute value of the sum of two things, that is less than or equal to the absolute value of the first thing plus the absolute value of the second. So that's by the triangle inequality. So we're investigating this absolute value. We've now found it's bounded above by this. I can use another property of absolute values. The absolute value of a product of two things is the product of the absolute values. So this is the absolute value of A times the absolute value of an minus A, plus the absolute value of B times the absolute value of Bn minus B. Okay, that again is just property of absolute value. You have to take the absolute value of the product of two numbers, you can take the absolute value of the first, the absolute value of the second, and multiply those two things together. Okay, why have we done this investigation? Why have we said that the absolute value we're interested in is less than or equal to this expression here? But you see, crucially, this expression, inside it, you see the absolute value of an minus a and the absolute value of bn minus a. The distance of the sequence elements an from their limit and the distance of the sequence elements bn from their limit. We know an is convergent to a and bn is convergent to b. So we know that if we wait around long enough, meaning look at high enough values of the index little n, this absolute value gets very, very small. It can be made smaller than any positive value x. And the same thing can be said for this one. If we wait around long enough, this absolute value of bn minus b, will become as small as we want. Okay? So that gives us control. We have great control over these. So we can use that control. We can use that control that we have to control the size of this thing, and that will, because it's bigger than or equal to the absolute value we're interested in, that will control the size of the absolute value. So I can use this control that we have, because an converges to a and bn converges to b, I can use that to achieve this step, and then we'll be able to claim convergence. Okay, so we let epsilon be any positive number. Remember, our argument has to work for any positive value of epsilon. And there exists a number n1 such that if n is bigger than n1, then the absolute value of an minus a will be strictly less than epsilon over 2 times the absolute value of alpha. Remember, here we're using the convergence of an to a. So we can require that this absolute value, the absolute value of an minus a, to be as small as we want. So here I'm requiring it to be smaller than epsilon over 2 times the value of alpha. The reason for why I'm choosing that size will become apparent shortly. We also know the same thing about the sequence Bn. It converges. So there will be some point capital N2 such that this absolute value will be strictly less than epsilon over 2 times the absolute value of beta. The reason for that choice is when I substitute these upper bounds in for an minus a and bn minus b here, the whole thing will evaluate out to exactly epsilon. The absolute value of alpha will cancel with that. The absolute value of beta will cancel there. You'll have epsilon over 2 plus epsilon over 2, so you'll get exactly epsilon. And that's the upper bound I want to arrange for this, for the absolute value in question. So if we let capital N be the maximum of those two, if we wait around long enough, if we wait around so that both of these inequalities will be true, then for every value of n bigger than or equal to this capital N, which is the maximum of those two, n1 and n2, the absolute value of the thing we're interested in, which is alpha an plus beta bn, minus alpha a plus beta b. Okay, we've already shown this is less than or equal to this final expression here. This is when we investigated it. found that this is absolute value of alpha times absolute value of an minus a, plus absolute value of beta times absolute value of bn minus b. But now, I know the value of little n is bigger than or equal to both n1 and n2. So I can substitute in these upper bounds. So this is going to be strictly less than absolute value of epsilon, sorry, absolute value of alpha by epsilon over 2 times the absolute value of alpha, plus the absolute value of beta times epsilon over 2 times the absolute value of beta. And this whole thing, you can see, just comes out to the value of epsilon, isn't it? The alphas cancel, betas cancel, the epsilon over 2 is epsilon over 2, so we've got exactly epsilon. So we just pause there and step back from the argument a bit. We declared that, I'll return to that in a moment. We declared at the top, given any value of epsilon, we have to find this point, capital N, that makes this inequality true. So here arrived an epsilon. The only thing I used about it was that it was positive. I know in the convergence of an, there exists this special number, capital N1, which has this property here, because an converges to a. I know there exists the capital N2, such that epsilon over 2 times the absolute value of beta will bound bn minus b. And so all I do is I just make sure that both of those upper bounds hold. So if I let for any value of the index n bigger than or equal to the maximum of those two, so here's where we found our capital N, it's the maximum of n1 and n2. For any such value of little n, the thing on the left, this thing here, is strictly less than epsilon. Okay. That was the result we had to prove. Okay. So we've got it. So that allows us to conclude so by the definition, we can now say that alpha times an plus beta times bn converges to alpha times a plus beta times bn. We know that to be sure because we've seen how the formal definition of convergence for both sequences combine together through the existence of n1 and n2 and the choice of n as the maximum of them. How they combine together to prove the formal definition of convergence for the new sequence, for the alpha an plus beta. So we now know that that property, the linearity of the limiting process, is safe. We've seen the proof of it, so we know it to be true now, so we can believe every application of it in treatment of finding the limits of given sequences. So I know I wanted to approach that very carefully, give you plenty of motivation at the start of why we're doing it, the reason we need to do it. It does require some study, okay? The side notes that I put, did I put a little side notes? See these little comments I do on this group. There is much to unpick here in order to gain a proper understanding of how to prove objects. Okay? It is complicated. We're taking a formal technical definition of convergence. We're playing fast and loose with it. We're using it as it applies to 2 different sequences and then combining it together to establish the definition for a new sequence. Okay? So there's, the thing to understand is to look at the proof and understand how we use the control of the sizes of an minus a and bn minus b, how we use that to exert the control over the new absolute. So it does take a bit of meditation on it, it does take study. You have to think through, constantly looking back at the definition, the formal definition of convergence, thinking how that operates in order to get a good understanding. So tomorrow we'll look to the product rule and the quotient rule, and we'll work through some examples of applying the algebra of limits theorem and some related books, okay, to open up the rest of the sequences tutorial. Okay. So we'll see some more applications of the formal definition tomorrow. Okay. How's our signature sheet doing? Who's got it? Good. Did everybody see it? Excellent. Good operation. Or maybe not. Okay, so if you haven't signed it,